suppose. All right, I've started the recording, and assuming that this talk doesn't go completely terribly, it will make it to my YouTube channel eventually, and I will let you know where to find that. So can everyone see the screen share? Everyone hear me? See me? Excellent. So I'm used to teaching in a hybrid format, so I've got all of the Zoomers on one window. I've got the screen share being recorded separately, so none of your faces or anything are part of the recording. I do have the chat window open if anybody wants to talk to me or ask questions while we go. That's fine as well. So in full disclosure, this is a talk that I initially wrote about 2 years ago to give, and when Danielle approached me about speaking to this group, I thought, well, I liked that talk, maybe I'll dig that back out. So this is a little bit dated with respect to the work, but it's something that I haven't had a chance to publish yet, so it is relatively new from that perspective. So a long extended title here, but the gist of it is trying to figure out how to operationalize all of the different ways that two variables that are each measured repeatedly over time can relate to each other, and what common choices that we use do and don't do in that regard. So associations in longitudinal data then, people usually talk about the type of associations as belonging to one of two levels, between persons versus within persons. And at a minimum, we would expect the occasions from the same person to have some kind of correlation because people differ from each other in their levels of an outcome on average. And so if that's true for both, we'll say a predictor X and an outcome Y that are both measured over time, then we would say, for instance, are people who tend to be higher on X than average relative to other people, do they also tend to be higher on Y on average? And that would be considered a between-person relationship, or what's known as level 2 in multi-level models in which occasions are treated as nested in persons, or macro level, if you want to talk about it that way. And that's the part of the types of relationships that you would have had from cross-sectional data, because between-person differences are always available even if you measure people at least once. The novel part that longitudinal data gets you, of course, is the within-person level, and at a minimum, this would involve variation around persons' means. So if I'm higher on my predictor X than I usually am, where usual would be defined by my person mean, then am I also likely to be higher on Y than I usually am? And so these are really the core concepts. Between person is more than other people as a reference, whereas within persons is more than usual relative to your own expected mean or expected trajectory. And this is all well and good for certain kinds of longitudinal data, such as for constructs that tend not to change as much, so observational studies, intensive longitudinal data, and that kind of thing. But in a lot of places, we're interested in measuring change over time, looking at prediction of change over time and relations of change over time. So how does that complicate the picture? Well, to the extent that variables that are measured repeatedly have individual differences in change, then that forces us to adjust how we talk about the results of these models and how we would go about operationalizing these distinct kinds of relationships. So for instance, if I'm interested, say, in a setting of older adults, measuring longer-term changes due to aging or other types of disease processes in health and cognition, it might be the case that between persons, people who are higher than others on health might be higher than others on cognition. But if we're talking about both of those variables changing over time, average might not be specific enough. We would have to think about an exact point in time relative to the rest of their growth or decline trajectory. So we would say that's an intercept relation, meaning that it's conditional on a particular point in time rather than just the average. But the extra piece of that that's available to be examined if variables have individual differences in change are the relations among those slopes. So do people who tend to decline less in health than other people, do they also tend to decline less in cognition than other people? That is also a between-person type of relationship, but it's a relationship of the within-person times slopes. So it's a bit of a mouthful, but the idea is that people differ from each other in two different ways. Each of those ways can potentially relate across variables, intercepts, and change over time. Then the within-person level has to be described differently as well. Rather than being higher or lower than one's usual level or average, then we would talk about being higher or level relative to someone's growth trajectory. So if I'm higher than my line expects me to be at this occasion on X, am I also likely to be higher than my line expects me to be at this occasion on Y? And if it's the same occasion, then that would be a concurrent relationship. You might also have questions about if I'm higher on X now, does that show up as being higher on Y later relative to what is expected in both variables? And so that would be a lagged relationship. So we can examine either of those types of relationships. It's also possible that those within-person associations in turn could have individual differences between persons as well. The extent to which being higher than my line on one variable relates to another, that slope itself could differ across people. And change over time is more obvious in some cases than others. In longer-term developmental studies, that would usually be one of the focuses of interest, but this type of time-slope relationship is also potentially something to watch out for or be interested in, depending on your perspective, in short-term relations as well. So if I have a daily diary kind of study where I'm just monitoring people's daily experiences, perhaps more than once a day, I might ask the same types of questions, for instance, relating health and negative mood over a period of days or weeks. And it might be the case that people who tend to be less healthy tend to be more grumpy than other people. So that would be a between-person relationship among the means of cross variables. But it also may be the case that when you feel worse than you usually do, you might be grumpier than you usually are, and that would be a within-person relationship. The idea of a time slope, though, could also show up in the ways that circadian rhythms, schedulings, and all kinds of other types of life events might create effects of time even when we don't anticipate it. So just as an example, there was a movie in, I want to say 1999-ish, called Office Space. Any fans of Office Space here in the house? If you haven't seen it, I highly recommend. But there's a classic quote from Office Space where someone is saying that he wants to go get some coffee, and another coworker says, "Sounds like someone has a case of the Mondays." Meaning that for this particular individual, they feel worse, perhaps they're in a worse mood, and they feel worse on their health on Monday relative to other days. So there's a Monday slope, if you will, operating on Peter, the main character in this movie. Now, it's also the case that there may be individual differences in the extent to which people have different outcomes on Mondays relative to other days. And if somebody has a Monday slope operating in terms of describing their relative differences in health, that might be related to the same idea of a Monday slope relating individual differences in mood as well. So just because it's not a long-term developmental study doesn't mean that there aren't necessarily time effects at play due to not just what day it is, but what day of the week or other kinds of factors like that. So the big picture is that I hope that what I have to say applies broadly across all different kinds of longitudinal data, not just data where the focus is explicitly on change over time. So then there's 3 different types of variability at a minimum that we might see in longitudinal data: between person differences in some kind of overall level, either a mean or a conditional intercept, between person differences in within person slopes, so slopes for change over time, slopes for other kinds of time varying predictors as well, and then within person variation describing how people vary around their predicted trajectory. So why are you off your line today is the way that I typically explain that. That's the type of within person variation that would remain. So what I have seen most common is that in theory, each of these 3 sources can have its own set of relationships across variables, but in practice, that's not always available because of choices that people make in terms of their estimation routines, as well as the choices they make in terms of how they set up the model. And so where this project originally came from was me having the same conversation repeatedly with several different graduate students and colleagues, where they were talking about fitting their longitudinal model, and they did person mean centering for this, and they wanted to talk about the results. And I was like, hold up. Like, how do you know that that's what you need to do for your predictor? Well, what do you mean? Well, if your predictor shows individual differences in change, then person mean centering is not what you want to do. What do you mean? So rather than continue to have this same conversation repeatedly, I tried to write a paper about it. And so this talk is based on me trying to explain why that is the case, that person mean centering is not necessarily what you always want to do for longitudinal predictors. So time-varying outcomes being treated differently than time-varying predictors is one problem. And the quotes around these are really air quotes because it all depends on the way that you're thinking about these variables and the roles that they have, whether something is a predictor to you versus an outcome. When both of them are measured repeatedly, either could be the other one. And the idea that time is still relevant, even in short-term studies, that you wouldn't necessarily expect longer-term change. There still may be patterns related to day of week and so forth that you would want to pay attention to, and individual differences in one's susceptibility to those patterns. So the end result of both of these potential problems is bias in the answers that you care about. So within-person relationships are not going to be recovered accurately to the extent that there are between-person slope relationships lurking in the data that are unmodeled. So I wanted to do a simulation to describe this. I had intended initially for it to be more of a demonstration than an experiment, but I actually learned a few things that I didn't expect out of it, so that's always a bonus. So in terms of the presentation then, what I want to do is describe the data that I simulated where I know what the right answer is, and then go through what would be a reasonable list of models that people might fit to these data to answer particular questions, and try to link across all the different ways that people describe these models with words, equations, and pictures, because that's getting increasingly complicated these days with more options available to model longitudinal data than we've ever had before. So those would include what I would call univariate approaches, where you have to designate one variable as the outcome and a different variable would be a predictor, and those would be estimated in traditional multi-level modeling software. There's also what I would call multivariate models, where we're using latent variables to represent the levels of variation both on the predictor side and the outcome side. And those options then allow us to have some more flexibility in terms of the relationships that we would specify, such as including autoregressive effects and cross-like effects of variables across occasions. And then finally wrap up with what I hope is some advice on best practice in light of real-world data complications that we all have to deal with. So the right answer then, the way that I simulated the data so that I know what I'm supposed to get back from all of these approaches, I have two variables, I'm just calling them X and Y, no missing data, and 100 persons. So it's a relatively small data set because what I have seen most in practice is the more occasions you have, the harder it is to obtain a large sample of persons in that case. So I have 5 occasions, and in my notation I'm using T for time at level 1, and I'm assuming at this point that they're all equally balanced, equally spaced, but they don't have to be. That everything that I have to say would hold equally well if you had another type of time metric where it wasn't equal interval. So the model that I generated is agnostic as to what is the predictor and what is the outcome. It's just 2 variables, X and Y. And each of these variables was constructed by having individual differences in an intercept, individual differences in a time slope, and a residual at level 1. So in the level 1 model, I've got my model for X that has a placeholder for the intercept, a placeholder for a slope for time. It's linear here, but it could be anything that it needs to be. Those 2 placeholders for each variable then are defined in the level 2 model. So we have a fixed effect and a random effect that goes with each of these. Fixed effect being what happens for the sample on average. Random effect meaning your deviation from that fixed effect, where we estimate the variance across people in each of those random effects. And then E at the level 1 model is usually assumed to have constant variance after we control for the random effects with no covariance, and that's going to be the case here as well. And the fixed intercepts were set to 0 because they really don't matter to the story. The fixed slopes were actually manipulated. And in terms of the variance components, I made it so that both variables were symmetric in terms of their relative amount of between versus within-person information. So I set the total conditional variance at time 0 to be 1, which then would give me an intraclass correlation of 0.6 if I had the random intercept variances at 0.6 and the residual variances at 0.4. And then I computed the corresponding time slope variance that would go with a slope reliability coefficient of 0.6, just as a benchmark that I picked. And this is based on work by Willett from the late 1980s. I can send you the formulas if anybody is interested. But the key idea here is that both X and Y have a signal to them with respect to intercept differences, individual differences in change over time, and a capacity for those things to be related. So I initially manipulated whether or not there were fixed time slopes in X and Y. I collapsed across all of that because it absolutely did not matter, because fixed time is always going to be a predictor in the model. So the key manipulation here, and what we want to watch for in terms of recovery, is 3 different kinds of relationships and whether they match. So at level 2, I'm manipulating the correlation between the random intercepts for X and Y to be either 0 or 0.3 in a correlation metric. I did the same thing among the random slopes. So a positive correlation of 0.3 or 0 in those cases. And all other combinations of random effect correlations were 0. At level 1, I manipulated the concurrent correlation of the residuals as either 0 or 0.3. So what we will see is that when everything matches, it's all good, but when they don't match, then the answers that we get back are going to be dictated by what type of model we set up and whether the model can accurately separate out all of these 3 different kinds of relationships. All right, so any questions so far? We doing okay? I know that's not cool for a presenter to ask in a talk, but I teach in this room, and so it's like instinctive. I'm watching the chat if anyone wants to talk to me. All right, I'll move on then. All right, so the choices then that people would typically go for in longitudinal analysis, what I was, my first class today was multi-level models for longitudinal data. So what I would call that is a univariate approach, because in a multi-level model setting, we would have to designate one variable as the outcome and the other as a predictor, and that designation then leads to them being treated in a different way. So the choices that we would have for modeling a time-varying predictor in traditional multi-level model way would be either using person mean centering, baseline centering, or detrending it, and I'll describe each of those in just a second. And the benefit of this approach is that it is very easy to implement in software. There's a whole bunch of different packages that will do it, including even in SPSS, which I've found that works pretty well. Multivariate models then is the other choice. So in this case, we would predict both Y and X as outcomes. Even if conceptually we're thinking about X as a predictor of Y, we would let the model partition its variability into between versus within, and then between intercepts, between time slopes versus within residuals. So you can actually trick univariate software into doing multivariate multi-level models. If you double stack the data, so you put X and Y into one column, then you can estimate essentially a bivariate model where all of it's being estimated at the same time, fixed effects and random effect variances and covariances. And you can look at relationships between X and Y in that tricked out multivariate model in the G matrix, covariances among the random effects, or the R matrix for covariances among the level 1 residuals. But if you don't want a covariance, if you want X to predict Y and potentially predict Y differently for different people in terms of moderation, controlling for other predictors, and so forth, then tricking univariate software is not going to be what you need. In that case, we need to move into something that is actually multivariate, where we can predict X as an outcome, predict Y as an outcome, and we can specify whatever kinds of relationships between them that we want. So in this case, we have the world of structural equation modeling at our disposal, the single-level version of it, as well as the newer multi-level versions of it. And I tend to use the term multivariate multi-level unless it has an actual measurement model to it. The examples that I have here have no measurement models. We're basically just dealing with observed variables and partitioning their variability into levels of analysis. I'm focusing on ML estimation, even though some of the more recent advances require Bayesian information. There's a good reason for that, which I will get to in just a little bit. So the first type of approach then, this is where the first thing that I would teach my students to do, for instance, is a univariate multi-level model. So let's say that we have Y as our outcome. I might fit a growth model that looks something like this, where Y has an intercept and a slope, and we let the intercept and slope have a fixed part and a random part. That's all good. But if I know that random effects, as they are notated by the U's in these equations, are actually the same thing as latent variables, and indeed they are, that means that I could set up this exact same type of model as a structural equation model of some kind. So I could use single level format, in which case the trick is just to reshape the data. So I'm going from a long data format where it's one row per occasion per person into a wide data format where it's one row per person. And then the exact same model would be described this way, and I have mapped on all of the parameters that we would have in the multi-level version of talking about it versus the structural equation modeling version of it. Rather than having the separate circles for the residual variances for each occasion, I just have the one box here because I've constrained their variance to be equal across time, so that there's a direct correspondence between the two. The only difference would be the method of estimation that's available to you. If you're in structural equation modeling and you want to use likelihood estimation, it has to be the regular flavor maximum likelihood, whereas in univariate multi-level models, you have an additional choice of residual maximum likelihood, or REML, that works better in smaller samples. We could also do the same thing as a multi-level structural equation model, in which case we're back to long data, and the only difference is the capability of modeling multiple outcomes at the same time and including either directed paths or covariances as you see fit. So the diagrams for those look somewhat similar, but just given that it's long data, we only have one box rather than 5 boxes for different occasions. So I have my time box, my y box, and I have a random slope indicated with the path between here itself is the source of this random circle here. But otherwise, everything matches exactly as you would expect. So if I were to put in a time-varying predictor, so in my mind, I'm thinking of y as my outcome, I'm thinking of x as my predictor, this might be the first thing that people would try to do. And if you learn nothing else about multi-level modeling, I would want you to learn that you cannot do this. This is what I refer to as the smushed model, otherwise known as a conflated effect, a convergence effect, or a compositive effect. There's a lot of different terms for the same problem. But basically what happens is that if you put in a time-varying predictor into the level 1 model directly and only estimate its fixed effect, then you are asking the model to create one parameter that has to do the work of 2. So for the same reasons that we would need a multi-level model in the first place for y, because we have to worry about how much of its variation is between persons and intercepts versus within persons over time, we have to worry about the same partitioning of a variance in x. And so when we only have one fixed effect, that's the same thing as saying that between person effect of that variable and the within person effect of that variable must be the same number. And that doesn't make sense either mathematically because they're on different scales, or conceptually because they represent different relationships for different reasons. So this is bad news. Anytime that a time-varying predictor has between person variation in it, this model is going to be some kind of wrong. What we need is to represent our predictor at every level of the model at which it has variability. So if it's just occasions within persons, then x goes into the level 2 model as well. If it were occasions within persons within groups, then x might potentially go into the level 2 and 3 models as well. So any level at which it has variance, it needs to become a predictor represented at that level. The question is how to do it. So here's one choice. If we did this in structural equation modeling, it would look like this down here as a single level model. It would look like this as a multi-level model, where I just have my box here that's predicting both the level 1 outcome and implicitly predicting the level 2 outcome. So this is a convention that I'm using to describe this smushed effect, that the relationship between x and y is being held constant across levels, even if we don't know if that's a reasonable thing to do. Most of the time it's not. So within multi-level modeling, you would learn some potential remedies to this, and I think the one that is probably most common at this point is referred to as person mean centering. It comes out of the group mean centering or cluster mean centering context for people nested in groups instead, where what we would do is take off the person mean out of the level 1 variable, and we would then stick that person mean in the level 2 model instead. So what we would try to do is essentially the brute force version of what happens on the y side. the person mean is directly analogous to what a random intercept would be for x, and the within person deviation at level 1 is directly analogous as to what the level 1 residual would be for x. Another variant that I've seen is, I call it baseline centering, where rather than using the person mean, you use the observed score at time 0 and subtract from that. And so that would then go into the level 2 model instead. And the idea here would be that at level 2, you're looking at the effect of initial differences in x as a predictor, and then change from that initial x as the level 1 predictor instead. So if this works, then the resulting level 1 coefficient, which is labeled as gamma 2 here, would be the within person effect, the effect of more than usual on x and y. And the level 2 effect would be the between person effect, the effect of having more x on average than other people. The problem is that neither one of these is really what I want. So person mean centering arguably would be the stronger of the two choices, but the timing is off. So I have a level 2 intercept that is at time 0 specifically for y, and I would be looking at how it is predicted by the person mean of x, not the time 0 value, but the mean. And in some cases, that's not going to make sense because of that asynchrony. Baseline value solves the asynchrony problem, but the baseline value is not just the intercept. It also has some of the level 1 residual still baked into it, so it's not ideal from that perspective either. So what this would look like then by adding these level 2 observed predictors in to separate out the between and within effects would look like this in a multi-level SEM diagram. So we've added in our level 2 box here, and it would have a level 2 box in the single level model as well. And I've tried to highlight the idea that we have a constrained level 1 effect by putting just one box for all of the arrows in the level 1 model. So the question then is, how well are these two approaches, person mean centering and baseline centering, able to recreate the 3 original relationships that I had introduced into these data? So there should be no relationship of my level 2 predictor with the time slope. That was never in the generating model. And because x doesn't have a time slope, individual differences in change over time in x are nowhere in here. They're not represented as an explicit term. So because I don't have an x time slope, I can't recover a correlation between the x time slopes and the y time slopes. So I expected that that would just be missed, and that's what was going to happen. I expected then that the level 2 effect of x would be a reasonable stand-in for the intercept correlation, although not as good given that it's an observed variable rather than latent. And likewise, that the level 1 fixed effect would be a reasonable stand-in for the correlation among the level 1 residuals. So here's what happened. This graph is going to show bias as the y-axis and everything for 3 different parameters. The level 2 slope that's supposed to represent the between person intercept to intercept relationship between x and y. The middle one is going to be the level 1 slope of x that represents the within person residual relationship between x and y. And then the last one here is actually the r square for the y slope variance specifically, which should have been pretty close to 0. And the first row here shows the condition in which there was no correlation between the time slopes of x and y, and the bottom one is when the correlation is 0.3. So with respect to the between person intercept relationship, big miss. So the green arrows are highlighting the conditions where everything matches. So all 3 relationships were either 0 up here, or all 3 relationships were 0.3 down here. And in those conditions, we get the exact right answer back from what the between person intercept relationship would be. When they don't match, though, they are off in a compensatory fashion. So if the intercept relationship was supposed to be 0.3 and the residual relationship was supposed to be 0, then what we get out as the level 2 relationship is downwardly biased. It looks closer to what the residual would be than what the intercept would have been on its own. The opposite happens if you change the configuration here. So what we're seeing is that the intercept relationship is being contaminated by the residual relationship, even though I'm already distinguishing levels of variability via person mean centering or the observed baseline. They both work basically equally badly. So this was something that was relatively unexpected to me because I expected the problems to come in with respect to the time slope, not the intercept. But the intercept here is not being recovered accurately in either condition with respect to the time slope relationship. The level 1 relationship is creating a new kind of bias. So if the intercept and level 2 intercept and level 1 residual relationship being put together is a conflated effect or a smushed effect, the term that I would use to describe this different problem is time smushing. So it's still a conflation of two different effects, but in this case what we have is that what I want to call within persons at level 1 is actually being contaminated by a between-person slope relationship that's unmodeled. And so in the cases where the time slope relationship is 0, the residual relationship is downwardly biased because it's trying to pick that up. And likewise, if the time slope is 0.3, the residual relationships are being positively biased instead. So there's a smushing together essentially of what should have been just within persons. Actually, the between-person slope relationship is creeping in there. And in terms of the prediction of the slope variance for y, I thought this should be near 0, but actually it turned out differently. So the negative values here you do see are actually negative pseudo r-squares. So the variance went up because of the smushed effect relative to what it should have been if the time slope relationship was the same as the residual relationship. So the take-home point then, person mean centering or baseline centering, if the x variable has individual differences in change, it's not going to adequately separate out the intercept relationship that's level 2 between persons from the residual relationship that's level 1 within persons. So one approach that folks have tried to address this problem staying within the univariate framework is what's known as a detrended model. And this has a long history of use. It used to be called slopes as outcomes in the 70s and 80s, I think, when it was invented. And it's the idea of, okay, well, if I don't want the slope for x to confound my relationships, let's just take it out by brute force. So I can estimate a regression model for each person's data separately, output their intercept, save that for a variable, output their level 1 residuals essentially around each person's growth curve, and save that as my new level 1 x predictor. So the x at level 1 per occasion has been detrended by each person's individual time slope from separate models for each person. And you can save the intercept that you get out of those individual analyses to use as your new level 2x. So if you do it this way, the good news is that it does work with respect to the level 1 relationship. So if you take out each person's time slope in x via a separate model, save the residuals that are left, insert those residuals into a different model predicting y, the fixed effect that you get out of those detrended residuals is indeed impervious to what it should be relative to the time slope. So that part was fixed. So the green lines here in the middle you don't see because there is no bias. But the bad news is that the relationship that you get by taking those individually saved intercepts and treating them as your new level 2 predictor, they're nearly as bad as just using the observed baseline. So we have the same pattern of compensatory bias where the between-person intercept relationship is not being cleanly separated from the within-person residual relationship, even if the residual relationship is being recovered accurately. And we have the same pattern of negative r-square values for the y time slope that reflect this idea of a time smushed effect. It's still operational. So at this point, one might be saying, hey, why are x's in boxes and y's are in circles? That seems awfully arbitrary, and you would be right, and I would agree with you. So one of the problems with this is we're trying to distinguish variability in x using observed variables, which is not going to be as efficient or powerful as using latent variables. So that's where the motivation comes in for what I would call multivariate multi-level models, or what other folks might just call structural equation models, where rather than trying to separate out the variance in X by brute force, we're going to treat it the same way as we treat Y. What you end up with in these models in terms of your level 2 effects, though, can be quite complicated. And I have a link to a paper here in which I'm focusing on M+'s switch from maximum likelihood to Bayesian estimation after version 8, where the exact same code gives you two different sets of level 2 model parameters, and trying to figure out which ones you get and what they mean can be quite tricky. So from this point forward, I'm not dealing with the multi-level SEM variant because of that problem. So this is what it would look like if you kept the same model for Y that we had before, our growth curve type model, but then we treated X as if it were also an outcome, where we partition its variability into a level 2 random intercept versus a level 1 residual. And so this would be called a bivariate growth model or a multivariate growth model. And I also point out that there is the relationship between the residuals from X to Y is implemented via what's known as structured residuals in the code. So you essentially take what should have just been the residual of each variable, save it as a new latent variable, and estimate the relationship between the new latent X and the new latent Y at level 1, rather than having it go between the original variables. The reason to go to that trouble is because if you do it between the original variables, what you get at level 2 is actually a contextual effect, not a between-person effect. The two are related to each other, but they tell you slightly different things. So the structured residual solves that problem. So then we have a more symmetric structure across X and Y here, which requires a little bit different notation. So I am using a between-within type of notation here to get at the idea of at level 1 we have prediction and leftover variability. So we have XW and YW, which then get decomposed as follows. So X has nothing predicting it at level 1 so far. Y has the time variable that we had before, but now rather than having some kind of observed version of X, we're using the model partitioned version of what would be level 1 variability in X directly. So one latent variable predicting another, and it's being given a fixed effect only in this case. And then at level 2, we can do the same thing. Rather than trying to figure out what kind of person mean X or baseline X or detrended X we can fit in a box and have it predict Y, we're going to have a latent version that's directly estimated by the model, so it's directly proportional, or parallel rather, from between X and Y. So we're having the intercept of X as estimated by the model predict the intercept of Y, as well as the slope for change over time in Y. So how well does this work? It turns out not very, because just translating from a univariate to a multivariate framework in how the variability in X is partitioned is insufficient, because our model still doesn't have any place in it for individual differences in change in X, and so we see the same compensatory patterns of bias as we saw in the univariate approaches. So here's the problem. For any variable, we can start with just a single pile of variance. As I say in my class, once upon a time there was an E. Before everything got complicated, when you first learned regression, there was an E at the end of the equation, and that's all you had to know. Well, the very first step in any kind of longitudinal analysis is typically to see how much of what we're calling E is actually consistent person mean differences, or cross-sectional variation, versus level 1 longitudinal variation that we would then call E for real. We would introduce a fixed effect of time, so linear, quadratic, piecewise, whatever you need to do, and that fixed effect of time would partially explain this E variability that's within persons. Well, if we want to allow each person to have their own version of that effect of time, a random slope, then where that variability comes from is this E. So in the same way that all of the variability was initially split into level 2 and level 1, the remaining variability that we were calling level 1 gets split again into what is level 2 and level 1. And so the idea that some of why people were off of their line is because the line didn't fit and they need their own line. It's a different kind of error, but it gets reallocated up here to level 2. So if we don't go through this second step of reallocating random variability in change to its own variance component, both of these two things are still buried in here. And that means any effect of this predictor is going to reflect at least two things and not one, as we had intended. So to fix it, the answer that you've probably guessed by now, we predict X in the same way that we predict Y. We make sure that all fixed and random effects of time are properly modeled in X before we see how X relates to Y. And the addition of that extra level 2 between person variance and slope then affords us to have another relationship. And so at this point, finally, we're able to look at how the slopes relate to each other because the model operationalizes each of them. So it would look like this in terms of SEM diagrams, where the new latent variable for X is right here. So how well does this work? Much, much better, but it's still not perfect. So I had expected everything to be all hunky-dory in adding the time slope here, and one of the questions that I wanted to ask is how much of it is allowing X to have individual change versus allowing X's individual change to relate to individual change of Y, because those are two different things. And in most cases, it looks like adding the time slope is insufficient. We still see some patterns of bias, although it's much better than only having an intercept. Adding the time slope doesn't solve the smushing problem because the effect of how X relates to Y is still being biased by that slope relationship that's unmodeled, although to a much lesser extent. So this is still, I think, the optimal strategy, but there may be situations in which you don't get back everything as cleanly as you would like, and of course that's going to be exacerbated to the extent that you have small samples, unbalanced time, missing data, and all the usual suspects. The slopes as outcomes. So what if we did the individual regressions for each person, outputted their intercept and outputted their slope, saved the detrended residuals for the level 1 predictor, and fit that to our univariate model? Nope. It doesn't work. So the level 1 relationship is accurately recovered regardless of what happens with the slope, but the other ones are all kinds of messed up. So that's no good. So to summarize here, they're ignoring the idea that the predictor has slope variance in it, that the predictor has two different kinds of between-person variability, not just one, is problematic because, first off, when we talk about between-person differences, if people change over time, then they rearrange themselves. So the idea of just having a person mean is insufficient to describe what the rank ordering would be of different people across time. The other is this idea that the variability that's contained in level 1 is unpartitioned. That's where the slope variance is going to be lurking. And so then any observed variable that contains both of these things is going to be trying to do the work of two different variables, much as the same problem as the original conflated or smushed effect with respect to the intercept at level 2 versus the level 1 residual. And then something that I think is maybe not as well understood, and this is actually a paper that I'm working on right now, is how these same ideas translate into the world of autoregressive cross-lag panel models. So in these sorts of models, the original variant of it would look something like this, where we're interested in how X predicts X over time, Y predicts Y, and how they predict each other. And this model has the same problems as the naive approach for time-varying predictors. It does not adequately distinguish between person variability in intercept, let alone slope. And so all of these relationships are going to be some smushed combination of multiple levels of relationship that have not been appropriately distinguished. And I note the same thing would happen to any kind of mediation model where you're not describing between person variability separately from within person. Well, folks have figured this out, and that led to a random intercept version of this model, which I think is still sort of currently the gold standard in at least applied fields, that you get bonus points if you fit the random intercept version above and beyond just the cross-lag panel model, where then we have a separate relationship between persons and the intercepts than what we have within persons of these autoregressive and cross-lag paths. However, does this fix the problem of hidden relationships among the time slopes? One might think that it could because of the autoregressive relationships working to sort of get at the same problem, they're trying to capture stability over time that's not captured by the intercept. And so if there's stability due to individual differences in change as a systematic component to the data, then maybe the autoregressive patterns would work. So I extended the simulation to look at these sorts of models. I know that we're running short on time, so I'll fast forward to the punchline. Basically, what ends up happening is that if you have time slopes in these variables and they're unmodeled, you get all kinds of craziness in the autoregressive parameters that come back. So like a type 1 error rate of almost 1 because slopes are not being modeled appropriately for change over time. In X, slopes are being modeled in Y, and so there isn't a problem there. The same thing happens in the cross-leg paths. You get bias all over the place because of the asymmetry in predicting growth from one variable versus the other, and all kinds of messed up stuff continuing for going from Y to X on the other side. So point of the story, it's not just the idea of the same occasion residual, but any kind of lagged effect, whether it's the same variable or otherwise, would potentially be biased from missing slopes and missing slope relationships if they vary across people. So that's the take-home message then, is the idea of which came first in terms of within-person relationships over time cannot be reliably answered until we have adequately represented all of the reasons how people differ from each other, not just in intercepts, but in change over time, as well as their effects of other kinds of time-varying predictors that in turn could have different relationships. So I have some sort of like recommendation-y slides and stuff like that, but I think it would probably be better to stop, and that way we have time to talk if anybody wants to talk to me. How's that sound? Yeah? I can see the clapping, so I think that means good. The Zoom environment is so crazy. Yeah, yellow hands clapping. I like those too. Just as long as no one has like a poop emoji or something, I think I'm doing all right. And yes, that is a choice. All right, let me, I'll leave the screen share up just in case anyone wants to point out a particular thing, but I'm happy to speak with anyone who has questions or comments, either in the chat or with your voices, whatever works out to be easiest.
I have a request.
Yes.
Just to see your recommendations. I want to see your recommendations.
Oh, you do? Okay. So I should keep talking then.
Well, if nobody's have questions, I would like to see your recommendations.
Yeah,
That's
sure.
just my...
Yeah, whatever would be most useful. So yeah, I can keep going. Just trying to be mindful of the time. So my big recommendation is that even if you have the idea in your head that this is my predictor and this is my outcome, to treat them both the same. So a logical precursor to examining how two variables relate to each other, or more than two variables, is to see how they each relate to time, and making sure that that part of the model is informed separately. So I see like people fit like, well, I fit the CLPM and then I fit the random intercept version. And it's like, well, how do you know that X and Y need the same structure to it? That's an empirical question. So that would be the big one, is to start there and see if X has individual differences in change. Because if it does, you need to be in multivariate model land of some kind. So this is true with respect to either long-term studies or short-term studies. Any type of study where we have variables over time can have effects of time or other time-varying predictors. So that's the big picture, is person mean centering is not going to help you if X changes too. And in a lot of longitudinal studies, X is going to change and Y changes, and the extent to which that happens together is going to be a question. So we need a multivariate model of some kind so that the variability in X can be modeled as accurately as the variability in Y, including intercept and slope differences. If your X predictor only has fixed effects of time, then you're good to go with person mean centering, because putting time in as a predictor of Y also controls for any effects of time in X, because it's the unique effect of X after controlling for Y that's going to be returned by the model. So then you do have your choice of whether you would use observed or latent in that case. So latent variables, better if you can swing it. But to the extent that you have smaller samples, to the extent that you have less variability between persons, these models are going to be noisier, I guess would be the right word for it. Related to that, most conventional SEM software does not have REML estimation, and it doesn't use methods of denominator degrees of freedom, so you'd be concerned about inflated type 1 errors in those cases. Having everything be latent also makes it harder to look at moderation. So if you have your level 2 relationship between intercept to intercept, and you want to see if that varies for people as a function of some other thing, then that's a latent variable interaction, which adds to the estimation complexity. Whereas like if you're in observed variable land and multi-level models, that's just another box. And so there's no extra complexity that is introduced in teaching, or the in introducing moderation. Can Bayes fix it? Of course, there's always that, well, Bayesian will fix everything. Maybe. To the extent that you have the right priors, or at least not the wrong ones, to the extent that the parameter estimates that you're getting out for your random effect variances are on the same, they mean the same thing. So one thing that bothers me about that is that like the mean or the median of the posterior that's given as your summary of like your random effect variance, that's not the same thing as the mode, which is what's given out of maximum likelihood. And to the extent that your posterior is skewed, mean, median, mode are going to continue to diverge. And so I think some of what people are saying as well, I tried to estimate this model in ML and the random slope variance blew up and I got it in Bayes. It's like, well, because you got a different estimate of central tendency in Bayes. And so I don't know to what extent those differences play out. And I think this is probably one of the main areas of research that is increasing in complexity and interest because of this idea that ML is going to break down at some points, particularly in small sample sizes. Using observed variables instead, easier, faster, probably not better, for the same reasons that we all learned that latent variable measurement is, a better representation of a construct than an observed variable. It's the same. There's research on this that suggests that if you use person mean centering, for instance, you'll get a downwardly biased estimate of your level 2 relationship to the extent that you have small level 1 sample sizes and relatively, small level 2 to some extent as well. Anything that's a 2-stage approach, I would not recommend. So anything where you're like saving, slopes and intercepts and sticking them in some other model, yeah, it worked for the level 1 relationship, but then the level 2 relationships were all jacked up, so I would not recommend that. That means that you would end up moving into some kind of SEM software to fit it. Single level versus multi-level. So single level SEM, I think, is more accessible to start with, but then you quickly hit the wall of limitations of real data. So unbalanced time is a big one. I know there's t-scores and M+. I have not found a comparable option in Lavon. So if anybody knows of one, please tell me if there's a t-scores version of Lavon to address unbalanced time. The structured residuals trick that you can do in single level SEM doesn't always work. And that means that you have to try to figure out whether your level 2 effects are between or contextual. Multi-level SEM is, I think, more flexible, but it doesn't solve everything. So you lose the capacity to easily judge absolute model fit. You lose some of the other, I think, transparency in terms of like having lagged effects unless you're willing to move to some of the newer stuff that's coming out with the dynamic stuff. And then, yeah, just another thing, be careful what you get. Because the only way that I ever figured out what M+ was giving me when it switched from ML to Bayes was that I had simulated data where I knew what the answer should have been and it wasn't coming back. And then I figured out it wasn't coming back because they were giving me contextual effects instead of between effects for some of the parameters, but not all. And that irritated me so much that I just pounded out a paper all about it. So that's the paper about that. So I think that it's a great option, but you have to be extra careful of what you're getting back out of it. So here are some references if you'd like to read more about all the things that I just said. So does that help, Emilio?
Well, I hope everybody, yes.
Yeah. Yep. Your question is, can I hear the other 10 slides? What else? Or 429 where I'm at, 229 where you're at.
Lisa, I just want to say thank you. That was such a clear presentation. I don't have any questions only because it was just too clear. You didn't leave anything left to ask about.
Thank you. I appreciate that.
Philippe looks like he's thinking. Philippe is thinking.
Well, I know, yeah, folks tend to be shy in a group, so if anyone wants to talk to me about this, please send me an email. I'm happy to correspond individually as well, unless you have something, Philippe. Hello to you as well, by the way.
About what that means for time series and lag science and so like Mike said, it's not so much that I would say, hey, I'm not agree with this, that, I agree with everything you said. I'm just trying to process what that would mean for some of the research that I'm doing with time series, with bar models and stuff like this.
Mm-hmm.
Well, I know that there's no easy fix, so I'm just trying to think about how long is it to keep doing what I've been doing.
Did you say how wrong it is? Did I hear that correctly?
I know how wrong it is. Do I really want to go? Do I really want to go and get myself into the trouble of making my incredibly complicated model more complicated? That was my thought. And it will take a couple of days.
Yeah, I do think that to the extent that those models don't partition all of the sources of between-person variability, then yeah, you're subject to the same potential biases that what you're thinking of as within person isn't purely within person, it's other stuff. And if that other stuff is related across variables, then you're potentially smushing multiple types of effects together into one parameter. So I think that if the data are that complicated, then you kind of don't have a choice.
Well, I mean, what if your goal isn't so much interpreting the parameters, but maybe, let's say, as an example, forecasting the next days. Here we go, back again. That was so if you change the perspective on maybe not interpreting these individual parameters, but making predictions on future data, or in another example where you maybe want to extract some lag and vector or regressive parameters to then get to the covariance matrix. How wrong is that covariance matrix? So you're looking at that moment. So this is kind of what I'm thinking about now. So how wrong are these elements?
I don't have a direct answer to that because I haven't explored these ideas in that context, but my instinct would be to say it's got to be at least somewhat wrong, because you're not adequately representing the mechanism that's generating the prediction. From what I understand, a lot of those models have a stationarity assumption to them, that if you have individual differences in time, that's kind of the definition of like not stationary, right? The variances have to change as people spread themselves out. And so not representing that explicitly, I would think that eventually the prediction would suffer as a consequence of that, maybe not immediately, but downstream. But again, I haven't explored that directly.
Yeah, so that would be, so the idea there is, if you have like dislocation scale models where you would have a header, you model the heteroscedasticity in itself, so you would address this spread or change in variance to some degree, because that would be another mixed effect model in that case.
Yes, that would allow you to make the variances change over time, but you'd also have to have the covariances change along with them. And so then I think at that point, then the complexity would be on par with what the random slope model would require to make all of that happen.
Yes, that's kind of the thing that I'm actually doing. So that's why I'm saying this probably takes a couple of days to process. Yeah. Okay. I think it was nice seeing you, by the way.
Oh, you too. Yeah, it's been a while. So,
Yeah.
okay. Well, thanks for having me.
Thank you, Lisa.
Thank you.
Thanks for being here.
I throw my book at all of my students all the time, so it's great to actually see you talk.
Thanks. Hopefully it doesn't hurt them.
Actually, mostly helps them more than it hurts them.
Yeah, so this, by the way, these ideas are in chapter 9, but they're like apparently not in it enough because I still keep having to have this conversation with my students, and so that's where I'm trying to make this into like a paper. But we'll see. All right, well, thank you, everybody.
Thank you, bye.
Good afternoon.
Likewise. I'll just start clicking around here. There we go. Goodbye.
Goodbye.